Hello. As it's noon right now, so good afternoon. This is a talk from a Red Hatter Giuseppe Scrivano about atomic system containers. You may have heard something about it from Dan Walsh's talk, but this is probably a much deeper dive into the topic. So enjoy the talk and welcome Giuseppe, please.
So hi everyone, and I've been working with Project Atomic for almost 3 years, and today I'm going to talk about system containers. Probably you're already familiar with atomic host, but anyway, I will give a quick introduction. Some of the concepts here will be useful for understanding better system containers. So I copied this sentence directly from the Project Atomic.io website. And in this sentence, this definition, there are two words that I think are very important, and that's immutable and container. So atomic host is based on the concept of having an immutable operating system. So whenever you want to deploy it, you install the entire image. You don't install single packages. And this operating system is immutable. So it's read-only. And all the system services run inside of this read-only image. And on top of this, applications run inside of containers. So this is what we have now. And this is where system containers will help. While system containers are quite generic, and they can be used on different systems. You can use on CentOS, you can use on Fedora. And they bring with them the usual benefits of running an application in containers, like bundling of everything that is required for running the program, to isolation from the rest of the operating system. On atomic host, they have some additional advantages, because we will be able to move systems from the immutable image to the upper layer where there are containers. This is an advantage because we will have a smaller image. A smaller image will increase both flexibility, as you can assemble your operating system as you prefer. You will have a smaller image, and on top of this, you add the pieces you want. And also, now whenever you want to install a new version of atomic host, you want to upgrade your version, what atomic host does is to first check out the entire new version on the side with the current deployment that you are running. And once everything is ready, you can restart the machine. So if we will have also less components here, it will also require less downtime. And so to get their job done, system containers use a set of already existing technologies. They use runc to run the container itself. As Daniel was saying, runc is the same technology used by Docker now. So it's the core part of Docker for running its containers. And we don't require another daemon or service for managing these containers, but we just use systemd. So you will manage them as a regular service, as you already do today. And for the storage of the images, we use OS3. OS3 is the same technology used on atomic host for storing the operating system itself. And finally, Scopio for copying the images from registry. Well, this shouldn't be Docker registry, just registry. So for the format of the image and the distribution, we use the same concept that I was saying before. We try to reuse as much of what is already available. So the system containers are distributed and built as OCI images. So you can use the same tools that you have today, like Docker build. And the metadata for running these containers is distributed as part of the image itself. we don't require a separate channel for distributing this, but you include inside the image itself. So in other words, converting an existing Docker container or container to a system container is just a matter of copying some extra files into this image. And very important, images are read-only. While this is a good pattern to follow for for any kind of container, that you keep your image read-only and only the storage is readable, so it's clear what is the image and what is modified. In system containers, this is enforced. It's not possible to have readable images. So I was saying that we need some files to add into the image for running a system container. And in this list, we see which files are required. So the first one is the most important, as it describes how the container will run. This is the OCI container specification for running the container using runC. The second one, if you're not happy with the default configuration file generated for systemd, you can provide your own. Then we have a manifest JSON for settings, various things for the image related to the system container. And finally, if your container requires some temporary files or directory to be present on the host before it runs, you can use systemd temp files. Probably you have noticed that this configuration files is in .template. So the reason is that they don't define a static configuration, but they define a template, and this will be used. So you can use the image to install different containers with different configurations, and your image provides a template, and these values will be assigned an installation time. When you install the container from this image, the template files will be used to generate the final configuration. But let's get more into details. So this is a simple Dockerfile for running an etcd container. And well, it's very simple. On top of Fedora, we install a couple of packages. We add some files that are required to run it. And finally, we define the entry point for running the container. If you have this, it's just a matter of adding a few files that I was describing before to the image. And this will make it possible to run this image as a system container. The benefit is also, another benefit is that the same image can be used in both ways. Still, you can use it as a Docker container, because these files will not change in any way how it used to work. And it can be used as a system container. This is our configuration file for running the runC container looks like. I don't get into the details because it's not where there is more to say, and also this is just a portion of the file. But what I wanted to show is how the template mechanism works. And you can see at the bottom of the file that we define some environment variables for the container. And this, we don't assign a value, but we say to get the value at installation time. Some of them are given a value by the atomic tool itself when you install. For example, name is the name of the container. Some others are expected from the user. So these variables are specific for running the etcd container. As I was saying, if you're not happy with the default configuration generated, you can provide one for systemd. The default one looks very similar, but here you can see also that we use again the template mechanism, the exec start and the exec stop for the service. That exec start variable will we'll get the value from Atomic, and it will be the command line to run runc. So what we do in this case is we specify the working directory where there is the destination on disk where we have the checkout of the container, and from there we launch the runc process. Manifest.json, well, it's not really used for various settings. At the moment, it's just for one thing, and it's to set the default values for the variables. If your image supports different variables that you can configure, you probably don't expect the user to specify a value for all of them. So you can give a default value here in this file. So if the user doesn't override the etcd name, it will be an empty string, and same for the rest of the file. Also, this is how the runc expects the container to be on the file system in order to be executed. And this is what's known as runtime bundle, or CI runtime bundle. So it expects the image under rootfs, and here you can see all the files required to run the image, and the config.json file. The config.json file is generated at installation from the image from the template that we seen before. This is the final file generated, and it will be used by runc. For the storage, as I say, we use OS3. If you're not familiar with OS3, just imagine it like a Git for binary files. And the two very important things to know for system containers is that OS3 manages the duplication of files. So it means you can add a file several times to OS3 storage, but it will be stored only once. And the checkout from the OS3 storage to the file system when you check out to a container, or for Atomic host when you check out to the operating system, is done using hard links. So it won't take additional space. So you can check out the same image multiple times, but it will just require the extra space for the inodes. But the file is stored only once. And if you're more curious about OS3, you can attend there is a workshop later at 12:30 by Jonathan LeBon. So in this model, we take advantage also of the Docker image format, where the Docker file is converted to a series of layers, where each layer is a step in the Docker file. We take advantage of this model when we pull images from a registry, as we are able to reuse these layers in case they are used by different images, in the same way as Docker does now. If you try to pull two images that have layers in common, the layers in common will be fetched only once. So we take advantage of this model by event mapping and in OS3 to the layers. We store this in OS3 branch. And we take advantage of the OS3 storage, because even if the same different layers add the same file, this is stored only once. An image through Scopio can be pulled from different sources. From a registry, that's the most common case. Or you can, especially if you are developing it, you can pull directly from the local Docker engine, or even simpler from a tarball. And this is the command that you need to provide for installing a system container. Well, here I described the steps, but this is what I was introducing before. This is a concept we copied from Atomic host. And as you can see, we created the checkout in a directory with .0 at the end. But then once we generate all the configuration files and we check out all the files, we create a symlink to this directory. This is very helpful for another feature that is Atomic updates. We support to update a system container in the same way, well, similarly to what Atomic Host does. Using this trick of the symlink, we create another checkout with a newer version of the container. We generate all the configuration files. So at the same time, you have the old version that is running. And while this is running, you created the checkout for the new version, created the configuration files. And then at this point, you can restart into the new version. We stop the service. We change the symlink to point to the new deployment, and we restart it. If something goes wrong, you can roll back to the previous version, well, unless the newer version doesn't destroy storage or something like that. But it should be possible to go back to the previous version. Future plans. For the future, I would like to see a better integration with systemd. For example, using dynamic users. At the moment, this is not supported. We can't define a system container that uses users that are not already defined on the system. Also, perhaps using a network D for setting up private network for the container. And another thing we are working on right now is a better integration with the operating system. We have noticed that many containers require to copy files on the host. And well, this model of system containers can be used as a more generic way to distribute files that needs to be installed on the system. But we don't want really to copy arbitrary files everywhere and pollute the system. But we are looking in the way to generate an RPM out of these files before it's installed to the system. So it will be possible to track the ownership of the files that are copied. So even if a file is coming from a container, you can still use RPM to query who is the owner of that file. Well, I have a quick demo of what I was talking about. So here I'm using a local registry running on my machine because I don't want to go on internet for pulling the image. And as we can see here, each layer in the image is pulled to the OS3 storage. We can see that there are under OCI image. Each of the layers we pulled, we stored in OS3 like a branch. And finally, we also stored the metadata of the image. It's the second line in the output. It's here. Here it describes the image. In each of them, instead, this what under OCI image describes the layer. Once the image is pulled, we can install it with the command I was showing before. So here we installed the system container. And here we can see we have a symlink pointing to the deployment with all the files. At this point, it's just a matter of running the systemd service. And we can see that we have we have run C and the etcd process running. We can see if it works like this run C exec is similar to Docker exec. It runs the command inside the etcd container. And here we can see that etcd is running. So I'm running here just a command on my computer to generate a new version of the image so that we will be able to simulate an update. At this point, we can we can try the update of the container. It's enough just to specify atomic update and the name of the container. So here we generated a new checkout. You can see that now we have two checkouts. /0 is the old version and .1 is the new one. After that, we stopped the service and restarted into it. Okay, sorry, just 1 minute left. I will do any question? Okay. Okay. So, well, I want to show the rollback.
Thank you.
Rollback. Okay, last thing. And with the rollback, we can get back to the previous version in case we are not happy with the updates. Okay, that's all for the talk. And any questions?
Is there a way to search and find which containers can be installed in the system?
We are working on that. We have a. Okay, yeah. So the question was: is there a way to search what containers system container? We are working on that. We are adding a new label so that it's possible to get this information even before you pull the container. You can query it directly on the registry.
So if Docker is using runc as well, so are system containers somehow seen by Docker?
Well, the question was, Docker is using runc. Are these containers seen as from Docker as well? No. The answer is no, because Docker keeps track of what containers are created by itself, so it knows which runc container is a Docker container. No. Runc inside of a container? Sorry, I don't hear. The question is runc a requirement for system containers? Yes and no. You can still use this mechanism to deploy other kind of images, like if you want to run a root, you can still use the same mechanism and just provide your own system deconfiguration file. So you specify how the application will run. And other questions? Seems no. Oh, yeah, one.
There are some containers like parcels local in the Red Hat registry. Are they already prepared this way, or are they in a different form?
They are not prepared yet from my knowledge, but I think it will be possible to use the same format. There is some work for moving existing super privileged containers to use system containers. Yeah. Last question. Sorry, which one? Can you say louder? No, but we are working now with the possibility of copying arbitrary files on the file system. So that will be possible if it's required from an image to have different services associated to the same container. Okay, that's it.